Welcome, folks, to our last TIVA-C workshop this semester. And this one is going to be on UART communication. All right, so let's get started with the presentation. Right. Oh, no, that's probably not. Is this good? Can you see my notes? Because in my internship. Showing PowerPoint only, right? Okay. It's the reason I'll just do it this way. Okay, anyway, UART communication. All right, so what is UART? UART stands for Universal Asynchronous Receiver and Transmitter, and honestly, true to its name, it does what its name stands for. Universal because it can work with any two devices that is smart enough to communicate. Asynchronous because it does not require the clock to synchronize data bits. Receiver or transmission because it's a two-way communication. That means it can receive and transmit, right? Again, it's one of the serial communication protocol for devices available. Actually, one of the many serial communication protocols, but it's in a special kind because it's asynchronous. And serial communication just stands for data protocols where data is sent one after the another. So it's just like a little array, if you can think. So if you can imagine, how you declare an array, it's like a stack of memory. So that's how you send the data sent one at a time. There we go. And it can be used for both wired and Bluetooth communication. The funny thing is you might still need to wire something, at least for the Bluetooth chip, if there is no Bluetooth supporting in one of your devices. Anyway, and these are the UART pins, right? It's also very simple. I think I had that in the previous slide. It's pretty much the most simplest one. You have two pins, transmission and receiving. TX stands for transmit. RX is for receiver. And again, as the name suggests, TX pin is used to transfer from device 1 to device 2. Now, there were other strong words for device 1 and device 2 I did not feel comfortable using. But if you're in engineering, you know what those words are. And vice versa for RX. There we go. Okay. And TIVA-C on UART. Of course, there's more information on UART on the data sheet than what I can show here. And really, most of that should be reserved for your classrooms because it talks about specific registers and how you'd go about them. But if you're coding UART in TIVA-C with TIVA-ware peripheral libraries, then you really wouldn't need to worry about it. That's one of the reasons why I haven't talked about much of anything related to the lower level details. We're just going to stay in the middle. Okay. Anyway, TIVA-C has 8 UART modules, UART 0 to UART 7. Each of them has TX and RX pins. And they can all operate independently and also in parallel. The only stipulation there is that you would have to do something like an RTOS most of the time. Because if you just do it with a while loop, what happens is one has to stop working before the other, right? Because that's the execution of program. It goes top to bottom. When you have something like an RTOS, which stands for real-time operating system, two things can work parallel. It's like you coding, it's like you typing and using your mouse at the same time, right? So that's two different things, but they're working the same way. Anyway, okay. And yes, GPIO pins may be used for multiple UART modules. We're going to be using UART 0 in our demo. It is somewhat special because it uses pins A0 and A1. These are pins that are not accessible to you on the board because they are reserved, and you have to sort of use them. I forget the word, but like in a certain way. So A0 and A1, they are reserved for the communication. If you use UART for that serial bus connection that you have with the TIVA-C, and that's what we use. That's what we're going to use. And on the right hand side, if you look at that, I'm going to move my camera. You have the modules and the pin information. And again, these are not the complete ones. These are only like some of the simpler ones out there. And also, this all comes from a website. I have referenced them, by the way, on the PowerPoint, on the notes sections, and this is all in GitHub. So you can definitely go take a look. And I would actually honestly recommend going to this website now. The only issue is that they do it in Q for the examples. So if you have Q, you want to use Q, it's a good way of going about it. All right. Last one. So now configuring UART via TIVA-ware library, as I was saying, it is relatively simple. especially if you consider the fact that, for Q or even assembly, you don't have to really specifically use registers. In Kill, you can use libraries too, but it's more rare. Again, programmer doesn't necessarily need to know about the internal registers and configurations, and that's basically true when we code, right, in C or C++ or any other thing. We don't really care about what happens on the lower level. So that's why APIs is preferred. And again, this demo also utilizes the utilities library of TivaWare. So what happens with TivaWare? There's more than one library. Most common is your peripheral ones, of course. Sometimes you have a bootloader, you have utilities and the other things, and they're all there. They're all given to you by TI to make your life easier. And I'm doing air hands here because it may not make your life easier because their documentation isn't exactly the best. Or sometimes you just can't read them or understand them for that matter, right? Important thing for, okay. Like the most important thing for us when we configure UART, at least with APIs, is to understand what baud rates are. Because they're the only way to synchronize data between two UART devices because it is asynchronous. So if you're using synchronous protocols like I2C and SPI, I think even HTTP, I think they use a clock. I don't think HTTP uses clock, sorry, forgive me. But at least I2C and SPI, they do use clock, right? So then we don't have to worry about baud rate there because you have a clock to synchronize the data. Whereas you will still have baud rates in those connections. It's just not as important as UART because in UART, it's the literal only way to synchronize data. And the baud rate for both devices, device 1 and device 2, has to be the same. Otherwise, you'll experience a lot of white noise. And actually, I can probably even demonstrate that in here. Actually, I will not be demonstrating that, but if you're doing it by yourself, just try changing baud rates. You'll see that you won't get anything, or if you do get, it'll just be a lot of white noise. And baud rate is formally the rate of transfer of bits per second. So it's just amount of bits per second. And most of the time, you will usually use 9,600 as a baud rate. And if you go throughout the libraries documentation that TI provides, they use like a 11,200, something like that. I mean, you can go with that. Most of the time, you use 9,600 anywhere online. Yeah, I mean, it's just a convention, I guess. Anyway, let's program now. So I will. Oh, that was my mouse fault. Sorry. I will stop. Get out of the PowerPoint real quick. Stop share, and then I will go to my code composer. Can you see this? Yes. So okay, and to whoever's watching, well, if you watch it after this, obviously, you will not see the same shell because I have provided a shell similar to literally this shell on the GitHub repository. There's also another main.c that's already completed. It is just not modularized and it's actually just more jumbled up. But that was what I used to actually come up with one of the demos for this demo. I cannot believe I said demos 3 times. Anyway, forgive my vocabulary here. In any case, we will go in coding. I also thought to use submethods like this. This is one of my favorite ways to code in C and C++, is when you declare a function and then you actually define the function at the bottom. Usually what happens, I think as I did with the PWM module, I just defined and declared and defined it on the top. Personal note, I like doing it at the bottom just because you can see all the functions being used, declared, and then you have main, and then you can define them later, right? But usually you'll just see them all being defined at the top. So this is kind of out of convention, I would say. Before I start, let me just talk about some of the variables I have here. So this is the baud rate at line 21. It's 9,600. And I have it here so that whenever we want to change the baud rate, it's easier to change in the code as opposed to just going down the code and changing it. And in line 22, we have clock frequency. This is 16 megahertz. So it's 1,600,000. Wait, I don't even know. 1 times 100. Well, that's 1,000. 1 times 100,000 to the million. Yeah, it's about 60 million. Yeah, this is 16 megahertz. This is for the crystal that's in TIVA-C. It's called precision oscillator crystal, something like that. And this also comes from a reference site here. I tried doing it my way. My way wasn't working. I'm being honest. There's quite a few ways of configuring TIVAs. Some of them don't even use this. Some of them just use registers. If you're doing it that way, you don't really even need that. Some do use driver level UART, right? If you go to the peripheral library, they will give you a certain way. Of course, it's more a pseudocode. You'll have to go code from there. But there's quite a few ways, and this one is like the easiest in terms of showing you, and also uses the least amount of code, at least from my perspective. In any case, let us go and this. So in the hardware setup function, we'll just be coding all the hardware things we need. And really, most of what I'm going to be doing here is similar to what I did with PWM, right? We enable peripherals, we configure UART, we're going to be also enabling port F, and then write to port F because we want to see LEDs. And also, if you're ever doing embedded programming, and you can't print to the screen, it's good to use something, some visual method of knowing that your code is working or something, or at least the program is working to a certain extent. And for us, we can use port F with the LEDs so that we know that it's working, right? Let me start. So SYS, system controls, SYS CTL stands for system control, peripheral enable. Okay, so there you go. That's one function. And we're going to be enabling the GPIO port A, right? Because port A0 and A1 are the TX and RX pins for UART 0. So perf GPIO A. Okay, there you go. And let me copy this real quick. And then now we're going to be enabling port F. So GPIO port F. This is where all the LEDs are, F1 through F3. Because F0 is like, it's just nobody uses. At least it doesn't have an LED. It's not that no one uses it. It just doesn't have an LED to use. And now I'm going to configure GPIO pin configure. Right. So this is in here. Now what I'm doing here is I'm configuring pins A0 and A1 for TX and RX. Sorry, RX and TX respectively. So A0 is the receiving pin, and of course all of this is in the datasheet, right? So and I also showed you in the PowerPoint A0 and A1. So pin A0, so U0 stands for UART 0 module. We have 8 of those, so UART 0 through UART 7. RX. Let me copy that so I don't have to type this real quick. And then now this is A1. This will become TX. Okay. So that configures the UART pins. Now I got to do GPIO pin type GPIO out. Right. And what I'm doing here is I'm saying pins PF1 through PF3 as an output. Also, what I noticed when I was doing this is that it seems that you cannot make the same pins as both out and also something else. So you can only do one at a time. GPIO out, output right there. Yeah, GPIO underscore port F. That's the base. It takes the base value, and also all of these are unsigned integer 32-bit values. That's what they represent. GPIO pin underscore 1 or GPIO underscore pin underscore 2 and GPIO pin underscore 3. So this configures pin 1, pin 2, pin 3. You can also write these just one at a time for all 3 pins, or you can use the 1-bit OR. I forget what. There's a word for this, just for the single OR bit, but it doesn't matter. You just do 1, 2, 3, and pin 1 is red LED, pin 2 is blue LED, and pin 3 is green LED, which is kind of counterintuitive because you go RGB, right? You think green is the second one, but it's not. And then now I have to enable I have to enable UART now, but just slightly different. We're doing system control peripheral enable. There is a function called UART enable that comes from UART.h, but we're not using that. In some other way of configuring UART, you have to use that. It's just this one you don't, because we're going to be using the utilities library later. SYS system control perif UART 0. Okay, so that's to enable UART 0 module. and then this is GPIO pin type UART. So now this is saying, hey, these two pins are going to be for UART, GPIO port A, base, GPIO underscore pin underscore 0, GPIO underscore pin underscore 1. That's A0 and A1. Because that's A is the base. Well, let me go to the next page here. I just have the code that I written on printed here so that it's easier for me to look and type. Okay, so now last bit is we have to set the clock bit. And that's just for the baud rate generation, right? That's not for like you to transmit data. UART clock source set UART 0, that's the base. UART clock PIOSC. So this value is saying, hey, which clock are we going to use? So there's two. You have the main clock, or that 80 megahertz clock, or you use the precision internal oscillator something crystal. I mean, I'm saying it wrong, but this is the crystal we have here, which is 16 megahertz. And I guess I can even show it in the demo. Is that the reason I'm using this clock is because if I use the main clock, I get a lot of white noise. So this is really not the reason. And in this just means that I'm setting that clock for UART 0 base. Okay. And now this is the only function from configuring that comes from the utility library. Config. So 0 is for UART 0. So this takes in the port. And this is the baud rate. We have baud rate, right? Okay, I believe this is what we have baud rate here. Let me copy paste that just in case I mess up the spelling. Okay. And this is a frequency. Okay. So that takes care of all the configurations. So now we can do it's a hardware setup like that. Now let's check if it runs. I mean, if it compiles. It does not compile, but we'll figure out why. There's 5 errors, which is fun. So there's too many arguments in a function call. Where is that line 141? There isn't line. Where's line 41? Oh, okay, here. But first one, this one. GPI, so control GPI now. Well, library. Oh no, I do. I have all of them. I mean, at worst, I'll just not do it function. I'll just put it on main. But like all of this works. Just trying to see if I spelled it correctly, because I don't know. We'll see. System control. Yeah, you're missing that. Yeah, somewhere. Yeah. Like I said. And then I copy pasted them after I typed each one. So okay, let me look at that. Okay, what did I mess up here then? GPIO port A underscore. Oh, it's funny how I typed it right here. But I didn't do it. Okay, let me see. All right, so that's 2 more errors, 3 more errors to go, which is here. I think all of them are the same error. GPIO pin type UART, GPIO underscore port A, PORT, A underscore BASC. So that's fine. Port A, GPIO, PINTYP. Okay. GPIO underscore pin underscore 0. Oh, you gotta put an OR, not a comma, OR, because we're configuring 2 pins, right? So what this basically means is, as you just saw, if you try to put a comma here where it's only really taking you 1 bit, a one port value. If you try to put 2, you have to put an OR bit. So it's saying this or that. So it's just both. Now let's see. All right, we're good. Okay, so that's the UART bit is completed. And then now let's go and configure all of the red LED and the other LED. So these functions right here are what we're going to be using on the demo to basically show the demo here that the UART is working. Okay, and this is a simple one-line function API call that just turns on the red LED for infinite time, really. As long as you power the TIVA-C, you'll run it. It will be on unless you turn the LED off. Pin right. Okay, this is called GPIO pin right. GPIO port F base GPIO underscore pin underscore 1, 2. So what this 2 is, again, let me do this here. So you have to understand this value here. This goes in binary. Okay, you have, so port F has 1, 2, 3, 4, right? 4 pins, right? So this is pin 0, pin 1, pin 2, pin 3. So red is pin 1, right? So if 2 value, so 2 in binary, 0, 0, 1, 0, right? So it talks to red. So red is on now, and basically because everything here goes inside a register, you're just basically putting a value in an internal register. If you look at the datasheet, that's what you will see. So when you put 2 here, it affects the red, and for blue, because blue is see, 1, 1, 2, 3. Blue is this value right here, and that value, what is that? That's 0, 1. That's 4. Yeah, that's 4. That's 4, right? In binary, that's 2 to 2. That's 4. And for green is this one, and that's 8. Right? That's 8. So that's what we're gonna be passing in here. All right. And also, if you were to plug in a wire, like a female to male wire or a male to male wire from the backside of the TIVA-C, you'll basically find that there is a voltage being passed on to said port. So there's actually active voltage being passed on the port too. That's what the GPIO pin right does, right? Okay, so now I got a GPIO pin right, GPIO port F base GPIO pin. Blue is pin 2. We're putting a value 4 here. And for green, GPIO pin right GPIO port F base GPIO pin underscore 3. This is value. Also, of course, to turn it on, right? You just need to have that 1 here. You could use something called bit masking, and there's more than one way of doing it. I'm just choosing the most straightforward way of going about it. You could also choose to put this in binary. I think you might have to say that the values you're entering is in binary, like something like 2, B. I think that is in Verilog. I'm not too sure about C. Okay, and in any case, this works. And to turn them off, you just have to write a 0 because as I explained, you just want zeros in all of them, right? So put a 0 here. So that's for pin 1. Put a 0 here, except this is pin 2. And put a 0 here. This is pin 3. Okay. So at this point, you have all of these functions working correctly. You're configured them correctly. Let's see if they're built. It does build. Cool. Okay. So now the last thing here is we gotta talk about this chart array with UART message. That's the message we're gonna be sending from this device 1. Well, device 1 will be the TIVA-C actually. That's the message that the TIVA-C will be sending to our computer, to this computer via COM, right? And because C doesn't really have a string variable, your best bet is to use a charter, right? And from programming, we know that if you declare an array like that, that means the size is sort of dynamic as you go type, right? It's not dynamic after function run, but it's dynamic when you're writing the function. You shouldn't really call it dynamic, but I don't have a better word for that right now. So I do have the string values written out earlier. I'm just gonna write that. in any case, I'll just do hello world, which is standard, which I would say is industry standard greeting for devices. I'll do please select from the options below. And I'm saying this because of our demo. So we have something there. One is turn on. And in this demo, we're only receiving one character to from UART. It's the easiest way to go about it. You can get string. There are functions in the peripheral libraries to get like the entire string values. It wasn't working for me, and I was like too tired, realistically, to like try to find it. And also, a character works just to demo this. Red LED, okay. Two option is for turn on. LED, right? We of course in the real world programming, if you're using any other languages, you should not be doing what I'm doing. It would be much easier for you to have like a couple of string variables, and when you're about to transmit them, just append them or concatenate them. Actually, that's a better word. And you just have to use plus signs for that. But you can't do that in C. So, well, you can do it. It's just kind of tricky. So, and I don't want to do that. Queen knows. Queen here. So which one? Queen was 3, right? Yeah. 4 would be turn off red LED, right? 5. Off LED. Okay. 6. Turn. Ooh. All right. Let's see if that's okay. I think that is okay. It builds. All right. So now onto the main function. There's only one thing we've said in main. So in main, this value is the one that prints UART printf. So this value also comes from the utility libraries. These two. You have to include both here because I don't know, because the IDE requires you to. That's my best answer. This is the C value where actually all the codes are real. Oh, okay, I know why. So whenever you have header files, which I'm sure most of you who are watching this would know, whenever you have the .h file, you also need a .c file, right? I know some of them don't have that .h and .c. It's just because I'm pretty sure what's happening here is that they have these functions defined. In here, most likely, some functions are being defined, but some of them, others are just being declared. Actually, what I just told you, it's more relevant to C++. All right, moving on. Because usually what happens is you're using object-oriented programming there. You can't do that in C. So when you do that object-oriented programming, you have .h define all the classes, and .c is .h to declare the classes, and .c to define said classes. In C, I don't know. Sorry. But something similar to that effect. I'll just say that. At worst, I'm wrong. It's fine. Okay, any case. So we just gotta send that, right? And then we'd use percent. No, not percent C. I'm sorry, wait. I think it's percent S. Yeah, percent S. And then UART MSG. So here's a cool thing about here, which I'm pretty sure most of you have pretty forgotten. The array declaration is also a pointer to said array in memory. So the name of that array is the pointer to the first cell of that array in memory, most of it stack, so you can use it that way. That's where this works here. You can't do that with 2D, I think. It's because it's so limited. But in any case, this is the best way to go about it. And this is no longer passing by reference. This is passing if you're passing in a function. If I remember correctly, this will be passing in by value. Will be passing in by reference. Most of the times you would be passing in by value. Yeah. Well, let us see. Okay, so that builds. Now we only have one other thing to build here. So we gotta go while. I'm gonna have an infinite loop here, -1. Or another cool fact. This works is because in C, and I think even in C++, any non-zero value would be true in a conditional. So you can have a negative number there, and it will still be true. So UART val. Yeah, sorry. I'm going to define a char value here. Just char value is UART Rx val. Okay. Call it that way. In the other main file, I have only called it UART val, just for value. And in here, I'm going to say UART Rx value val equals to UART get C function. And this also comes from the utilities library. This is literally saying, give me one character. This will just return the character. It doesn't take in anything, but it will return the character that was received by UART. And I'm going to now write a switch statement. Okay, switch, because it's the easiest in terms of an infinite. It's the easiest to both see and also know what's happening. Because what we're going to do is we're going to have cases from 1 to 6 as we typed in 45. So a switch statement is the easiest because we only have one character to determine that, right? To determine which one gets executed, UART val, Rx val, okay. That's a switch statement. Boom. Case. Oh my god, I don't like that at all. Okay, there you go, case 1 because it's a character one. I have a feeling it might still work if I just do 1, but just do this. Because sometimes a character and a single integer, they can sort of be intermixed. It has to do with the NCC values and anyway, too much to deal with right now. Turn on, turn. And even the way I have named these functions, right? The way you name these are sort of convention for JavaScript and even Java. You want the first one is camel case, but sometimes you don't do that in C. Most of the times you actually don't care in C. But anyway, do it that way. It's easy to read. Right. Case 2, turn on, spelled it wrong, turn on blue. Break. I have to do break every time, just because in the switch statement, if you don't put break, it will just execute till the end. And we didn't want that. In case 3, turn on green. Boom. Right. Okay, we got 3 more cases to go. Case 4 is turning off red, right? Turn off red. Boom. Break. Case 5. Turn off blue. Right, okay. Case 6. Turn off green. So in the last one, because this is the last case, it doesn't matter if you have break or not, because like you have nothing else to go down, execute further, but just for the sake of the flow and the structure, I put a break there. Okay, boom. It is, there are errors now. Nice. It wouldn't be a coding session if there are no errors, right? Let us see. Okay, unresolved symbols remain. All right, which one? Oh, these symbols. Undefined symbols. Turn off blue, turn off red, turn on green. Interesting. Oh, because I spelled them all wrong. It's funny. It says turn red on, and I put turn on red, of course. See, I am my own detriment. You know, like other people have actual coding problems. I just have a typing problem, essentially. So just put that in here and just make that blue. like whenever I'm coding, most of the time it just goes on figuring out like petty compiler errors, which are caused by me because I don't type things the same. It's every time the same. Anyway, turn red off. Okay. All right, red off. So okay. Last one. Wait, see if this works. Cool. It doesn't work. I mean, not that it doesn't work. It's So can we change cameras now real quick? How do I do it?
So you gotta switch your camera.
Oh yeah, I just did that. Okay. Deep tech. Whoa. All right. So we just gotta look over here. I mean, yeah, it's so bright that the LED can't be. Well, I think you'll be able to see the LEDs here. So what I'm gonna do now, I do know that I'm no longer shared. I have to, well, the code that's already uploaded to the TIVA-C is gonna work, but for the sake of this project, I'm gonna upload the code again. So
I can have to share again if you want.
no, that's fine because I'm just writing the code back, so it doesn't really matter. Oh, but I would need to share the screen too
Sure. Yeah, absolutely.
because the UART. Right. So for folks who are watching for a UART, you do need some kind of serial communication program like PuTTY or TerraTerm. I think TerraTerm is like easiest to use, I would say, but also it's the most restrictive. PuTTY is like you can just write your own COM and baud rate. Can people even see my screen? They cannot, right? Hold on.
You can share now.
Okay. I'll just share the whole screen here. So if you can see here, I have TerraTerm. I'm using COM6 because UART0 uses SLR's virtual serial port, which is the port this is this port, okay? So it's using the wire. And baud rate by default for TerraTerm is 9,600. But to prove that, let's go here, set up serial port, and you can see that it's 9,600. Okay. And I have uploaded my code here. So if I do reset, it should show up. There you go. So the transmission from device 1 to device 2 has been activated. Now let me turn red. If you can see a red LED just lit up there, I know it's supremely bright in this room. Well, see, whenever you watch this, you have this, you have the awesome privilege of just pausing the video and going back a frame, yeah? So you can see all the options for the TIVA. So option 1 was to turn on the red. Now I'm gonna turn on the blue. Red and blue make purple. This is like the best exercise you can have to figure out your rainbow colors. If you do 3 again, it's white because you have all of the RGBs on. Option 4 is to turn off the red. So blue and green sort of make a cyan blue color here. If I'm even saying it right, I think you can see it. You see that? Yeah. Mm-hmm. From where I'm from, we call that sky blue, but you know. Then 5 green turns green off, and 6 turns green off. Okay, and you can keep doing that 1, 2, 3, 4, 5, 6. You know, like I think red and what? Oh yeah, red and green make yellow, right? Yeah, there you go. Yeah, I'm not gonna get perfect because, like, see, in the real world, what you would do is you would use percentage of these values, but because you can't really do that with the TIVA, I mean, I think you can. It's just you would have to have the PWM module example that I showed, like in session 2. You would do it that way. You would just basically use PWM to modulate the intensity, and you could in theory just have different intensities of purple and stuff. The only issue there is you can't do that with a while loop. You would have to use something like RTOS, just because cause I try this with the while loop, and what ends up happening is it will stop. If you have red and blue, red and green on, it'll do red first, then do the green. So there's only a split second where it actually probably might even work, and if any at all. But yeah, that is literally it. Actually, also one more thing. I'll show you the white noise. So can we go back to this? Okay. I'm gonna go back to this here. So the white noise part, if we remember, so we're not going to be changing the baud rate. What will change is the clock source, because that clock source is being used to generate this baud rate. So, right, so I'm going to do 80 here instead of 16. And the clock source here, I'll use main. Okay, and you'll see that it does compile. It doesn't compile. It is undefined. Nice. It's okay. Hold on. Now this is the probably didn't, but in any case, the best way to do this. Can they see my file screen? Or they can't?
No, they just see the season.
Okay, here. I'm gonna stop sharing and share my entire screen again. So the best way, whenever stuff like this happens, you know, when you're actually coding, you go to your resources, and because the clock source set is actually from a peripheral library, we'll use here, okay? And then we'll go to UART. Where's UART? Somewhere here. UART somewhere here.
Oh, it's 30.
Oh, yeah, see, I can't. Thank you, Matt. I'm Matt. See, you and that sound the same so to me sometimes. So I'm saying, just confused. In my defense, it's just the same spelling except for M and N are replaced. And like they sound the same. You are, there you go. So I'm trying to, so instead of main, I'm trying to do system. Again, I spelled the wrong word. Like I said, I am my own determinant here. So it should be system and not main, okay? Oh, well, I should just show you that. Okay, so this is what the function does. As I said, right, it uses unsigned integer 32-bit and 32-bit base. And U32 is the base address of the UART port. I'm sorry, I'm looking at the wrong. This is the one we're supposed to look at. Because we're trying to set the clock, not get the clock. But it's the same thing, it's still system. So this is what we have, right? UART clock source set. You have 32, the UART base, and this is the source clock source. So this is the base address of the UART port, which is UART 0. And this is the clock system. Earlier we used the precision internal oscillator, PIOSC crystal, which is 16. We're going to use the main now. And let us see if it compiles. It does compile. And I'll build that here. You don't even have to focus on the camera because it's right now. I'm going to show it's going to happen in the UART screen. I'm going to hit reset now, and all of a sudden you won't see this. Or at least it shouldn't, because it didn't. It's UC equals. You see that? Nowhere in our code did we write equals. But there's equals here. Because that's white noise. It's not even equals. It's like a 3 R lines. But that's what we call white noise. It is data is there, but the UART here, which is device 2, doesn't understand what is being sent because the baud rates are slightly missed. They're not the same. And the reason they're not the same is not because we set a different baud rate, but because we have a different clock frequency. This works with this. You would have to figure out which clock frequency works best with with the baud rate. So that's kind of why UART is tricky sometimes. But if I pause that, if I go 16 here, right, 1.6, and instead of system, we use PIOSC. I believe that's how it was. Okay, now let me build that. And let's go look at TerraTerm again. Okay, so now if I hit reset, there you go. It says hello world. And the reason hello world is here because of the previous execution stopped here. So it just starts from there. In any case, there you go. That completes the UART demo. Oh, last thing before I go. So all the steps here, right? You can actually use a external chip, such as an HC-05 to use Bluetooth to talk via UART. I mean, only thing different would be you use a different UART port here, use a different base. One of the bases, can I go? One of the bases from here, right? And use the correct pins and stuff. And ready to then configure your baud rate and clock source. It should in theory work. Now what ends up happening when you try to put it in practice is it takes a lot of time. Sometimes it does work. Sometimes it works and sometimes it doesn't work. But yeah, good luck to y'all out there, and thank y'all for watching and coming. Peace.